Well, previously in the video, you've seen how we've been able to mill stock round. Now we're going to take a closer look to show you how you can get the optimum cut. Now let's take just a moment here and talk first about stock preparation. You can see we have two pieces here. One, of course, we've left square, the hub's mounted on the end. The other piece is 8-sided. We've simply taken the piece and cut the corners off on the table saw. The saw blade is simply set at a 45-degree angle. There are several advantages to having the stock with 8-sided with the corners off. One is you'll have less sawdust. The second one is you actually have less wear and tear on your router bit. And the third one is if you have a larger diameter stock, you're going to arrive at that round result much faster. There are occasions when your part calls for a square section. Then of course you don't want to mill the 8 sides. The preferred bit for this operation is Magnate's bit number 2704. It's an 1.25" diameter surface planing bit. The reason we use Magnate's surface planing bit is because it's completely flat on the bottom. The industry standard for surface planing bits calls for a 1-degree taper. That works okay on flat stock, but it's really not an acceptable cut when we're milling stock round. As a general rule, when we're milling on the Legacy, we're down the center line of the part. Now when we're milling stock round, we prefer that you bring the router in from the side and come into the 1/2" mark. When we're using the bit number 2704, the optimum cut is 1/2 inch off of center. Now the router bit cuts in a clockwise direction, and you can see that as we're offset a 1/2 inch, we get the optimum cut cutting with the grain. And you can see that as the router bit gets moved over center and it makes the cut, it's cutting across the grain. Therefore, it's going to create tool marks both on the front and on the back side. Now, of course, to begin with, you're going to put your stock in the machine. Bring your bed up so that the workpiece is high enough that when you plunge the router down, it's going to be able to reach it. If your design calls for a taper, then of course we want to raise and lower either end. You can taper from either end of the machine. It's preferred that you lower the tailstock side so that the part now stays closer to the router bit. There are actually several methods for milling stock round. The first one, we're going to use the spindle shaft handle. You'll recognize that the machine has two handles. One, of course, is your drive handle. It has a square hole on it. The spindle shaft handle, you'll notice, has a rectangular hole. That rectangular hole fits on the end of this drive shaft where the index gear is. We'll disengage the gears by releasing the pivot arm. And of course, now the index gear is available to us. Unlock the knob here, and in place of the index gear, we'll put the spindle shaft handle. If you're using larger diameter stock, then of course the router bit's going to come right off the end of the material. We have a drive center here, smaller diameter stock. We don't want to run into that. So we want to bring our router up in here and set a stop, in this case at 2 inches. We spoke previously about having the router bit set a 1/2 inch off center. Let's go ahead and bring that in and set a stop. Now we know that when we come to that point, we're exactly where we want to be. To set the plunge depth, we want to rotate the workpiece, find a flat spot, bring your router bit in, and just plunge down until it sits on the surface of the wood and lock it into place. Of course, you want to be sure and lock your plunge bar. Now with everything set up, we're going to make a test cut. Bring the router bit off to the side. We want to plunge down. We're going to rotate the workpiece in a counterclockwise direction. That will allow the workpiece to come up under the bottom of the router bit. And of course, we're going to bring the router in from the side as we make the cut. Now let's take a look at our part. You can see it's nice and round. We do have one area right here that's got a little bit of a flat to it. The reason for that is if you haven't mounted your hub perfectly centered on your part, or if your workpiece is not completely symmetrical, then of course you're going to get a low spot. Well, we can fix that by simply setting the plunge depth to this level now and recutting the part. Now if we just want to get the part round like we've done here, we just simply need to set the plunge depth and recut that. If it's critical to you that that part be a certain dimension, you may want to get a set of dial calipers and measure the part, and then of course use a set of feeler gauges to readjust the plunge depth. Okay, so let's go ahead and reset that plunge depth to that flat level on the workpiece. Set your plunge bar, come off to the side a little bit. Now the theory here is we're going to rotate the workpiece counterclockwise so that the workpiece comes up under the surface of the router bit, and we're going to advance the router about 1/8 of an inch at a time for each rotation of the workpiece. Now you can see the advantages of this technique is of course it's real fast and easy on the setup, real simple operation, nice clean cut. The disadvantage of course is at some point as you move that router down the length, you're going to run out of arm length here, and we have actually a technique that we'll teach you here in a minute about how you can get around that for your longer pieces of material. First let's talk about this. We have a piece of material that's square. We want to do that transition from square to round, and therefore of course we don't want to cut the corners off. So let's talk about that now. Now we're cutting from square to round, so we're going to get a lot more chips in the process here. So we're going to hook up our dust collection. On the back side you can see we've got our vacuum there on our dust port. Got our shield here that will slide onto the front side of the router. That'll help contain the chips as well. They'll hit that shield and drop into our dust bag. The rest of the machine is already set up the way we were previously, so let's go ahead and make the cut. Now let's take a look at the part here for a minute. First of all, you can see we have a nice clean cut on this edge. This edge that we're cutting into here has got a little bit of tear out. That's because we're climb milling the material here. The router bit's cutting here, but down here as it rotates it's undercutting the material, so therefore it's tearing it out. Now we can actually clean that up by cutting from the back side here, and you can see then of course it's going to give us a nice clean surface. The other thing is, if you'll notice that we have a bit of a radius here. If we want to clean that up and actually bring it square, we simply need to bring the router bit directly centered over the workpiece. Since we want to clean up that front edge, we're going to remove the stop here on the y-axis and pull the router to the front side of the machine now. And we want to set a stop here on the x-axis. This is at 8 inches is where we're making that cut. And the operation is essentially the same. We're going to bring the router in from the side, this time from the front side of the machine. Plunge down, we'll start the router up, and we want to rotate the workpiece, this time in a clockwise direction. You remember last time we were counterclockwise. We still want to bring that workpiece up under the material. And of course we'll do that as we bring the router in from the side. Okay, let's take a close look now at what we've done. Because we brought the router in from this front side now, you can see we've eliminated the tear out that we had otherwise, and because we brought it all the way in, we've squared up that shoulder. We have a transition from square to round now that's just squared off. Here, of course, is because the router bit is still back off center. So you can determine how you want that to look. This next technique, we want to show you an equally easy way to mill stock on longer lengths, right? Instead of being able to slide that router down the length of the workpiece and running out of arm, we're going to simply take the split nut now and lock it onto the lead screw. And now as we rotate the workpiece, again, we're going to do that counterclockwise. We can advance the router with the other handle. and it's simply rotating both handles at the same time. Let's go ahead and make the cut. You can see that we get an equally nice finish, and it's a very simple technique. So the obvious advantage to this technique is our part can be as long as we want. The disadvantage might be for you initially, this seems just a little bit uncomfortable and natural to you, but as you do this a couple times, you'll be very comfortable with it. Let's show you a technique now where we'll actually use the gears, and you'll simply use a single handle to advance the router and to rotate the workpiece. For this technique, let's refer to the gear chart on our headstock. On this particular operation, we want to use the half-inch pitch using the 0.25 gear reduction set and the A drive gear. Now, the 0.25 gear reduction set is optional on the model 900 and 1200. It's standard on the models 1800 and 2000. It gives us this range of pitches. The A drive gear is the largest drive gear available to you. We have the machine configured with the 0.25 gear reduction set, the A drive gear, and in this case we've used the right-hand directional gear. That right-hand directional gear will allow the workpiece to rotate in a counterclockwise direction, therefore bringing it up under the router bit as we spoke about earlier. And the other advantage of that is it will kick the wood chips back to the back side of the machine near our dust collection system. We'll start by leaving this X-axis split nut open so that we can cut around the end, and then once you've done that, lock the split nut and advance the router with the handle. You can see, of course, that we've got a nice finish here. Now, because we're using a half-inch pitch on here, I can actually feel just a slight ridge there, ever so slightly. Because on the other two techniques, we're using a finer pitch, we actually get a finer finish. For this final technique, we'll show you how to take advantage of the linear drive motor. To do this, you'll want to use the optional 0.25 gear reduction set and the A drive gear to give you a half-inch pitch. Now, to start the cut, we're going to leave the split nut open, let it cut around the end, and then we'll lock the split nut. Now, you can see the finish. It's really not as smooth as you can get it because we're using that half-inch pitch in the motor. It's going to give us just a little rougher cut. We can get the optimum finish by letting the motor rotate the workpiece and then sliding the router about 1/8 of an inch at a time down the length. Let's show you that now. We've reset the plunge depth to just a little bit deeper here. We're going to go ahead and let the motor rotate the workpiece, and we'll leave the split nut open and just slide it now about 1/8 of an inch each time. Now the advantage of this technique, of course, is that you can get the smoothest finish anywhere along the length of the machine. Let's take a look now at milling multi-sided pieces such as square or 6 or 8-sided, any number of sides. But first we want to talk a little bit about a common problem that the Legacy solves really easily. A traditional method of woodworking is to take your rough stock and get it all cut and sized the way you want it, trued up using your planer and your joiner, and then take that material and stick it in your lathe or your mill. The problem, however, then becomes of being able to center that workpiece into your lathe. Okay? Well, the best thing to do is to just get beyond that and take your rough stock, mount a hub on the end of the workpiece, just start rough, put it in the machine, mill it round, do your turnings, and then while it's in the machine, go ahead and cut your square up your ends as well. Let's take a look at these two pieces as examples. Obviously this one's been cut, milled to 8 sides. It's got a round detail here and a square section here. This square one as well. And you can see they're also they're perfectly centered and concentric to the part, all done on the Legacy. We've already milled this material round. Let's go ahead now and take a look at the technique, a close-up look at the technique for milling this, the flats on here to make this area square. Now let's just recap here. What we've done is we've taken that surface planing bit and climb mill on this back side here so that we get a nice clean edge here, and we bring it in each time we're just coming in a little bit more, about 1/2 of an inch is maximum, and then when we get to this side, of course, we're going to climb mill on this direction here, cutting this way. So we've gone this way and now back this way, and you can see we've got all those surfaces nice and clean and all squared up to our part here. Now let's take a V-groove now, V-groove bit, and just come in here and create a pommel. That's a transition from this round to this square area. The plunge depth for this cut is simply made by taking the tip of the bit and setting it on the round of the material. And we've locked the router into place. We're going to bring the router onto the back side here and rotate the workpiece, of course, clockwise into the router bit. One of the great benefits of having the Legacy ornamental mill in your wood shop is the ability to create turnings without the use of a lathe. Because we're using a router and router bits, we have a couple of advantages. One, of course, is it's safe, it's very controlled, and you also have the repeatability of the profile of the router bit. All 4 parts, all 4 table legs are going to be exactly the same. You also have the added advantage of being able to lay out your part before you ever make a cut. Using the Legacy Design Kit, we have router bit templates that show the profiles of the various router bits that are available. We simply use those profiles to position and to draw the shape of the cutter. Now we have a Legacy Design pad that indicates the Y and the X axis that corresponds with the machine, and so now you know position of the cut and also the depth of the cut. Well, let's go to the machine now and take a closer look on how to get the best cut when creating turnings. We can use the spindle shaft handle to rotate the workpiece, and we can use the X-axis lead screw to lock the router into place and then position it where we want. There are two different types of router bits for creating turnings. Let's take a look at how to set the plunge depth for the router bit that has the shoulder. Now we'll just move the router bit off to the side and then plunge down until the shoulder of the router bit hits the wood. If you're using a router bit that doesn't have a shoulder, something like a core box bit, you'll set it up just a little bit differently. You want to make sure that your router is positioned exactly centered over the workpiece and then plunge the router bit right down on top of the workpiece. At this point, you'll want to set the depth of the cut. We found a set of feeler gauges to be a useful tool. Simply take the desired width and place it under the plunge bar and lock it into place. That gap determines the depth of the cut. For this technique, we're using Magnate's bit number 3952. It's a large diameter router bit. It's 2 inches in diameter. Being that large, we don't want to take too much material at one time. So here's the technique. Position the router along the X-axis at the desired point. Here we've used 3 inches and lock it into place. Now, so that we don't want to hit the wood, so we back the router off to the back side here and plunge it down and lock it into place. Now we're ready to rotate the workpiece in a clockwise direction into the side of the router bit and bring the router in a little bit at a time as we get over center on the workpiece. Now you can see we could make that cut from either the back side or the front side. By coming in from the side, the point is you get control over the router bit and you make the clean cut. By cutting from the back side, we actually throw the chips into the dust control. Now we want to take just a minute here and show you how to control tear out. What we've done is repositioned the router and we're going to reset the depth. We're going to go just about 1/8 of an inch deeper than what we were before and make a second cut. You can see here that we're getting tear out on this one side. It's a nice clean shoulder on this front side. We approach the piece from the back side and the router rotates in a clockwise direction. Therefore, it's giving us a clean cut as it comes into the wood. However, on this back side, it's tearing out. If you need this shoulder to be clean, then you'll want to approach it from the front side, and of course that's going to cut into the material here, and you'll get a nice clean shoulder on the front. So here's the key. If your design calls for a clean shoulder, make sure that you approach that shoulder from the proper side, either from the back side or the front side. If your machine has the linear drive motor, you can rotate the stock through the gears. Because we're not trying to create a spiral pitch, any of the gear sets will work. Let's just turn the machine around here a little bit so you can see it from the operator's side. Leave your split nut open and slide your router into place. Here we're at 6 inches. And now lock your stops, one on each side. Turn your motor on. Make sure that the workpiece is rotating in a clockwise direction so that it's rotating into the router bit. We're going to make the cut, again, coming in from the back side. Now the nice thing about the motor is you can control how fast the stock's rotating, and then of course you're going to bring the router in a little bit at a time to make the cut. Now let's take a look at how to mill the rope design. Rope is traditionally 2 or 3 starts, with 3 starts being the most common. The pitch should be roughly 2 times the diameter of the stock. These 2 parts are each 1.5 inches diameter with a 3-inch pitch. This particular piece is a 3-start rope and this is a 2-start rope. And you can see they each have a 45-degree angle. As a general guideline, this 2-to-1 ratio will give you the 45-degree angle, which is very common in rope molding. If we look at this tapered sample, you can see that the larger diameter creates a tighter angle, whereas the smaller diameter results in a greater angle. As you can see, this ratio can vary, but if you stick to the 2-to-1 ratio, it will always feel correct. For this sample, we'll make a 3-start rope on 1.5 inch diameter stock. Let's start by looking at the formulas. With the stock being 1.5 inch diameter, we'll use a 3-inch pitch because that fits the 2-to-1 ratio. So now with a 3-inch pitch and 3 starts, we'll plug these numbers into the following formula. The spacing between each cut equals the pitch divided by the number of starts. We know the pitch is 3 inches and the number of starts is 3, therefore the spacing will equal 1 inch. In this case, the spacing is the diameter of the router bit. So we'll use a 1-inch diameter rope molding bit, Magnates bit number 7581. Now, if you're starting with square stock like you see here, you'll want to go in and cut the corners off on the table saw or mill it round like we've done here on this piece. Then set the gears using the standard gear set and the B drive gear for a 3-inch pitch. Plunge the router bit down until the shoulder of the bit is resting on the material. With the plunge depth set and the router centered over the workpiece, 0 on your y-axis scale, lock the x-axis split nut onto the lead screw and you're ready to make the cut. If we look at this part, you can see that we have 1-inch cut right here and it's formed 1/2 of the bead. We'll simply move the router bit over 1 inch, which is the diameter of the router bit, to form the second half of the bead. That will be our second pass. The third pass will be right next to the second. Having made the first cut, we now need to synchronize for the second cut. We put the router in the groove and we'll move it over 1 inch to form that bead. For the second cut, we want to resynchronize the router bit. We do that by pulling the router bit up in here and setting it into the groove that we just previously milled. Okay, now see where you are on your x-axis scale. I happen to be at 11 inches. We want to lift the router bit up, slide it over 1 inch, the diameter of the router bit, and lock the split nut onto the x-axis screw. Now drive it back to the beginning point, plunge down, and we're going to cut now from the tailstock to the headstock. It doesn't matter which direction we cut, but whatever the first cut was, you want those consecutive cuts to be the same. Let's go ahead and make the cut. There's our first cut, the second cut to form the first bead. Now this third and final cut will be positioned 1 inch over to form that second and third bead. Once you slide that router out of the way and you don't rotate that handle, you should just be able to bring your router back into 12 inches, which is where you started the last cut, and lock it into place, and that'll give you your third and final cut. Now if in fact you have rotated that handle, you'll want to resynchronize into that second cut and then move it 1 inch the diameter of the router bit. Let's make our third cut. Go back to the beginning here now. And that completes our 3-start rope. Now let's take a look at how to make the barley twist design. A barley twist will have 1 or 2 starts, with a single start being the most common in antique furniture. If you look at this single start barley twist, you can see that the ratio is 1 to 1 to 1. That is to say that the diameter of the part is equal to the pitch and also equal to the spacing, or in this case, the diameter of the router bit. As you can see here, the diameter of the router bit equals the pitch. Therefore, it forms the bead as it moves from end to end. For this part, we're going to make a 2-start barley twist. Now, our stock is 1.5 inches diameter. Therefore, we're going to use an 1.5 inch diameter router bit, and because we have 2 starts, we're going to need to use a 3-inch pitch. To start off, we're going to cut a cove at 3 inches and at 9 inches, and we'll use that same router bit to cut the barley twist between those 2 coves. We're using Magnate's bit number 7554. That's the 1.5 inch barley twist bit. We're going to plunge the shoulder of the router bit right down on the surface of the workpiece and lock the plunge bar. There's our cuts, 3 inches, 9 inches, and we'll cut the barley twist between them. To create the 3-inch pitch, we have the standard gear set and the B drive gear. We've set a stop here on our y-axis so that the router bit's cutting right down to 0 on our workpiece, and then of course you want to make sure that you lock the split nut on your x-axis. We're starting right here at 3 inches. Let's go ahead and make the cut. Now we've made that cut, and of course it's a shortcut, so because it's a shortcut, we're just simply going to open that split nut up right there at 9 inches, that's where we stopped, and slide it 1.5 inches to 7.5 inches. That's the diameter of the router bit, and now we're set up for that second cut. Let's drive it back here to the beginning. We always like to cut the same direction. You'll get a cleaner cut that way. I like to come off to the side when we plunge down, start it up, and let's make that second cut. Well, there's our 2 parts. They're both 1.5 inch diameter stock. They both use an 1.5 inch diameter cutter. This one, because it's 2 starts, we have doubled the pitch to give us a 3-inch pitch. This is a single start. This one's cutting to the right, and this one's cutting to the left. You can see that creating the barley twist is really a very simple process, but yet it creates a very elegant design. Well, one of the more fascinating designs to create on the Legacy is the hollow spiral. Real simple in its theory, but a little difficult, can be a little challenging at times on the technique. If you set it up properly and you take advantage of some of the things we're going to teach you here, you'll be successful. Well, there's a wide variety of various hollow spiral designs that you can create. We're going to create ours based upon the 2-start barley twist that you've seen presented earlier in the videotape. Again, we're using a barley twist cutter, 2 starts to create the splines, and then once we've got the splines created, we're taking a straight cutter down into the center. The pitch stays the same. The only thing that changes is the router bit. It's a straight cutter into this section right here, plunging down into the middle. To create the 2-start barley twist, we used an 1.5" diameter cutter, a 3-inch pitch to give us the 2 starts. Now when we started out with the barley twist, we cut a cove at 3 inches and one at 9 inches. What we don't want to do is start our hollow spiral at the 3-inch point. We want to come in about 3/4 of an inch. So we're going to set our stop at 3 3/4 on the front side, and because this one was set at 9 inches, we're going to start at stop at 8 1/4 on this side. Now we have set our optional thin stock support into the machine here, and what this will do is help us to support the splines as they're being cut. Just bring the jaws in and clamp right up against the workpiece there, and you can see that as the workpiece rotates, the thin stock supports it. What happens is as we remove material here, it weakens the splines, and so we want to be able to support those. You'll find that you'll be much more successful if you use the optional thin stock support. Well, we want to set a stop right here at 8 1/4 inches on our back side. And we mentioned earlier that we want to start the cut at 3 3/4 inches. Well, we're not going to use a stop to do that. We're actually going to lock the split nut onto the lead screw and drive it back past that 3 3/4 inch mark and then bring it down and advance it. The idea here is gears inherently have backlash in them. It causes a pause in the part. And we want to remove that, and we do that by, as we come back, we go forward again, and then we'll plunge down and make the cut from there. To hollow the part out, we're going to use Magnate's bit number S263. That's a 3/8 inch 2-flute straight cutter. We simply plunge the router bit down in between the splines, lock the split nut onto the lead screw, and it should track right in the groove. Ultimately, we want to cut down through the middle of the part. So we've set the plunge depth so that we're slightly below the center line. Now, of course, we're not going to cut that much at one time. We're going to cut about 1/8 of an inch at a time. So we've set our plunge depth. We lock the split nut onto the lead screw. Let's drive it past that 3 3/4 inch mark, advance it to the mark that we want to start at, plunge down and make the cut. And you can see there that once we've gone all the way down into the middle, we'll simply move that router bit over 1.5 inches into this groove here. That's the same diameter that we used in the router bit. We positioned it 1.5 inches. Well, right now we're at 7 inches on our lead screw. We'll slide it over 1.5 inches to 5.5 inches, lock it on the screw, and drive it back to the beginning. Again, you'll want to pass that 3 3/4 mark, bring it back forward, and make the cut. Fun design, there's our hollow spiral. Let's take a close-up look at using the indexing system to create flutes. There are two methods to do this. One is cutting from the top, the other is cutting from the side. Here you can see we've taken our stock and milled it down to 1.5 inch diameter. We've used Magnate's bit number 3952, which is a 2-inch classic spiral, and milled a cove on each end. Those are just transitional pieces. We're actually going to mill the blind stop flutes between these two coves. The simplest method is to use a plunge cutting bit like a core box. You're cutting down the center line of the part and milling from one end to the other. The second method is to use a side cutting bit. It has a longer shank, reaches in from the side of the workpiece, and makes the cut from one end to the other. The obvious advantage to using a side fluting bit is you can cut those flutes on any curved contour or profile. You can see that it has a bearing on it. That bearing simply follows the profile of the workpiece. There are three methods for laying out your flutes. The first, of course, is simply trial and error. You put a part in, put a router bit in, and you make the cut. You index to the next position, whatever you determine that might be, make that second cut, look at the piece and determine whether or not you like the spacing. There are two other methods that may work better. The second method is to calculate the number of flutes based upon the following formula. The number of flutes on the part can be found by determining the circumference of the part and then dividing that circumference by the width of the flute plus the spacing between each flute. Now if we take a close look at this part here, we see that that's the width of the flute and that's the spacing between the flute. We find the circumference by using pi, which is 3.14, and multiplying that by the diameter of our stock. Or circumference equals 3.14 times, in this case, 1.5 inches. Therefore, the circumference will equal 4.71 inches. Let's just throw some numbers in here and see what we get. If we have a circumference of 4.71 inches, and let's just say that we have a 1/4 inch wide flute with 1/4 inch spacing, we're going to take 4.71 and divide it by 0.25 plus 0.25, or 4.71 divided by 0.5 to give us 9.42 flutes. Obviously, we can't create 9.42 flutes on our part, so we need to either round the number up to 10, round the number down to 9, or down to 8. Now 8 fits into 24 positions, our standard index plate, into 24 positions 3 equal times. So we could use 8. If we choose to use 9, we'd want to go to our optional 36 position indexing plate. The number 9 goes into 36 4 times. Therefore, we would use our indexing and create our flutes every 4 holes. Now my favorite method for determining the number of flutes on the part is to use the Legacy Design Kit. This allows me to actually visualize what the part's going to look like. It gives me the depth of the cut, the width of the cut, and the spacing between each cut without having to go to the machine and make the cut, waste a little bit of time and material there, or to fuss with those complicated formulas. Now the design kit is laid out so that you can actually determine the diameter of your part and use that particular diameter to draw with. It's also laid out in 4 different quadrants based upon the indexing plates that are available. Here you see we have a 36 position indexing plate, and at 8-inch diameter part we have gone in and we have drawn the flutes, and now we know the depth of the cut and the spacing between each cut. For this sample that we're going to create, we're going to mill 8 flutes on our part. It's 1.5 inch diameter stock, so we're using this area right in here, and we're going to use this quadrant right here. It's 24 positions, which coincides with our standard indexing plate. We're going to use Magnate's bit number 3952, just the tip of that bit right there, and you can see we've drawn that in, and there you see we have now a cut made every 45 degrees on that part. Let's go ahead and make the part. To set up for this sample, we've locked our stops, one on each side of the router, so that we can control the length of each flute. We also have positioned our router so that it's centered exactly over the top of the workpiece. Now we want to set our plunge depth. we're going to set the tip of the router bit right down on the workpiece, just like that. And then, of course, we want to set the depth of the cut. In this case, we've determined that our depth will be 75 thousandths. We're using a feeler gauge, and so we set the spacing. Of course, we need to release the indexing pin. Just lock it on the end, and of course you'll want to lock the pin into one of the holes. It doesn't really matter which one, because the part's round, you can start anywhere. Before we make the cut here, there's a couple things we want to talk about, little techniques. One is, as you plunge the router bit down, know that if you sit there, it's going to burn the wood. So you want to plunge down and then slide the router down to the other stop, the other end, and then come back. The idea here is if you cut one way and cut back the other, you'll cut evenly on both sides of the material. Once you've made that first cut, bring your router up, and now we're cutting 8 flutes, and we have a 24 position index head, so we're going to cut every third hole. Let's go ahead. There you have it, 8 perfect flutes. Doesn't get any easier than that. Now keep in mind, this is one of the few times that you actually cut the part one way and then back the other way. As a general rule, we always cut the same direction. But in this case, what we've done is we cut down, loaded the bit the other way to cut the other side. It just kind of cleans that flute nice and clean on both sides. Let's take a look now at creating reeds on our parts. Reeds are just the opposite of what you see on a flute. A flute is a groove. A reed is essentially a bead along the length of the part. There are 2 techniques for creating reeded parts. Let's take a look at those now. The simplest cut to form the reed is to use a point cutting bit like you see here. You're cutting down the center of the part, of course, from one end to the other, and you're using the tip of the router bit. Now, it's not necessarily the cleanest of cuts because you can see as it rotates, it's really just dragging that tip through there. The one thing you don't want to do, unlike the flute, is cut from one end and back down to the other. On a flute, we generally do that. On a reed, we just want to go one way. The cleanest cut you'll get is with a side cutter, a side reeding bit that you see here. And it's simply rotating on the side of the workpiece and creating that cut. As you can see on this sample, the side reeding bit not only gives you a cleaner cut, but it also allows you to follow a curve. Like flutes, there are 3 methods for laying out your reeds. The first, of course, is trial and error. The second is the formula that we'll talk about here in a minute, and the third is the Legacy Design Kit. To form the reeds, we're using a side reeding bit in this case. You can see that the radius of the cutter, if it's 1/8 of an inch, then the diameter is going to be twice that, or 1/4 of an inch. As you make the cut, it's cutting half of the reed here and half of the reed here, and then as we index the part, it completes the other half of the reed and begins to form the next reed. And so you're looking for the complete diameter of the reeding bit. To determine the number of reeds on the part, we need to find the circumference of the part that we're cutting and divide it by the diameter of the router bit. We find the circumference by using pi, which is 3.14, and multiplying that by the diameter of our stock. Or circumference equals 3.14 times, in this case, 1.5 inches. Therefore, the circumference will equal 4.71 inches. If we look at a reeding bit with 1/8 inch radius, that's a diameter of 0.25 or 1/4 of an inch. We now take our circumference, 4.71, and divide it by 0.25, or the diameter of the router bit. And that leaves us then with 18.84. That's the number of reeds we would get. In this case, we want to round the number off, 18 being the closest. To get 18 evenly spaced reeds, it would require the optional 36 position indexing plate. In that case, we would simply index every other hole. Now, if we want to stick with the standard 24 position indexing head, then 18 is obviously not going to work because 18 doesn't divide evenly into 24. So let's try a larger diameter router bit. Let's look at 3/8 of an inch diameter. 3/8 in a decimal is 0.375. So we're going to take 4.71, the circumference of our part, and divide it now by 0.375. That equals 12.56, or the number of reeds. In this case, we can round down to 12. 12 reeds would come out on our 24 position indexing plate going every other hole. My favorite method for determining the number of reeds on the part is to use the Legacy Design Kit because it's very visual. You know exactly by the drawing what the part's going to look like. The numbers may come out right on the formula, but you don't know if it actually feels the way you want it to look. And so I like to lay the part out in a couple different scenarios using our design kit. As an example, we've taken our Legacy Design Kit here and drawn out the 3/8 inch diameter router bit. You can see there's the router bit. However, because we're using such a small diameter stock, 1.5 inches in this case, and creating 12 equally spaced reeds, it's going to give us, with that bigger cutter, a bit of a point here on the ends. And we decided then that we may like the smaller diameter cutter, the 1/4 inch cutter, using the same number of reeds, 12, on that 1.5 inch diameter. You can see it's a more natural looking reed, although it may give us just a slight flat. This is the one we're going to go with. So you can see that the design kit gives you a distinct advantage in that you can actually see what the part's going to look like and not just going by the numbers. Well, we've taken our stock now and milled it down round to 1.5 inch diameter. We've added a little cove on each end using Magnate Spit number 3952. That's that 2-inch classic spiral bit. And we'll actually cut now again from the side from one cove to the next and make our reeds. In order to set the depth of the cutter, the easiest way is to simply take that part out and set the depth of the cutter based off of the dead center on our tailstock. With our plunge depth set, we want to make sure that we lock the plunge bar into place. That's the depth of the cut right there. Let's pull this out of the way here and reinsert our part. Now once we get our part in, let me just talk about this for a minute. We're going to cut from cove to cove, of course, and we've set a stop here so that we're going to cut right into the center of that cove. Now because we're cutting from the side on the back side of the part, we want to actually cut from the tail to the head. The reason being the router rotates in a clockwise direction. In that case, we're going to climb mill the part. If we cut from the head to the tail, we would then be undercutting the material, and that gives us a rougher cut. So the cleaner cut is to climb mill. So let's bring that up in here, and let's plunge down, and we're going to set our bearing against the part. So we plunge down not all the way, but just put the bearing right on the part, as you see there. Now the y-axis needs to float in and out as you see here. But what we want to do is bring that bearing in until it touches the part and then set the stop. That determines the depth of the cut. We're all set up now. We want to make sure that we plunge down to that previously set depth. We're going to cut again from the tail to the head, and we're going to hit every other hole on our 24 position indexing plate. Now remember, on our design we had indicated that we might see just a little bit of a flat on our part, and sure enough we've got that there. That'll require just a little bit of sanding to take that off, not too much effort at all. But I got to tell you, using the Legacy to create reeds and flutes is a whole lot better than using your chisels and gouges. So you can see then that either using the formula or the Legacy design kit, we can calculate for any given diameter. In the case of a tapered part, obviously we have a larger diameter here, a smaller diameter here. We calculated for the center part of the diameter, the mean, if you will. And you can see on the larger diameter it's going to come into a little bit of a flat. On the smaller diameter it comes up to a little bit of a point. In any case, the reeds all come out the same because we're using the indexing. Now, on the case of this part that's got a little bit of a curve to it, we would plan for this area right in here in terms of our circumference or our diameter, and then just let the reeds come together up here as the diameter comes together. You can also use a Legacy to mill flat stock, such as picture frames and moldings, that type of thing. What you need is to solve the problem of holding the stock. In this case, we have an optional horizontal bench vise that you can pick up and mount to the rails of the machine. It uses a cam lock setup to hold the material. We also have an optional linear molding table. This allows you to mill longer lengths of material and feed it through as a fence on either side. So it's a handy little product. If you wish, you can build your own table. You simply use 3/4 inch MDF, and it sits in here and mounts to the adjustable bed rails of the machine. You'll want to cut your material 14 7/8 inches wide, which is the width of the rails of the machine here, and then you want to draw a center line down the length of the table. And then we want to drill some holes right here that line up with the channel of the rail here and countersink them. Now the hardware to mount the table comes with your machine. You'll see these locking plates that slide in the channel here. You have some flathead screws here that you just fit inside there and screw that down, and that'll of course hold the table solid so that it doesn't lift up. Now we've left these screws just a little bit loose so that it still slides back and forth and in and out on the rails. It's still fixed so that it can't come up, but nevertheless has some movement. What we want to be able to do is align the 0 mark of our scale here with the center of our line on our table. We'll use a point cutting bit here. In this case it's a V-groove bit, and we simply bring it in and set it right on the line there, and then just slide your table so that that line aligns with the point. Once you get that positioned over center, lock one corner into place there, slide it down to the opposite end, get it aligned up where you want it, and then lock the other 3 screws into place. And that'll secure it to the rails. There are several different methods for laying out the design of your molding. In this case we're going to use what we think is the simplest, and that's just simply using your design kit here. Now we have, for our sample here, we're going to use 3-inch material that's 1 inch thick, and we've just blocked out a little section here that reflects the dimension of our piece, and then of course we're going to use our templates to lay out the router bits. Okay, here's our design kit. You can see that we've laid out one router bit right here. That's the bit right there that we're going to use. We're actually going to use 2 router bits to cut this sample for you so you can see how it works. The second bit we're using is this 1-inch classic plunge bit, and so we're just going to draw that profile right next to the first one. And there you see, that's the molding. That's what our molding will look like. The great part about the design kit is that it not only allows you to visualize the design of the piece that you're creating, but you can also see where your cuts are made. You see that we have bit number 3934 here, this first one. It's centered right here at 3 inches, and so we bring the bit in at 3 inches and we make the cut. This second cut router bit is bit number 1274, and the center of that bit is right in here at 2 1/8 inches. So we're going to make a cut at 2 1/8 inches and one at 3 inches. The first cut will be at 3 inches. We're going to use double-faced tape to secure the material to our table, and once we get that, we just line that edge with the center line. Now you can see we've got our board set right here along the center line. We've got our router bit right at 0, and it's right on top of the edge of that material. We want to make this cut over here at 3 inches, so we'll just pull that over right there. And you can see then that that cut's going to be made right there along that edge at 3 inches. To set the plunge depth, you want to bring the router off to the side a little bit and then plunge down until the shoulder of the router bit hits the material. Now with that plunge depth set, we want to make sure that we lock the plunge bar. Okay? Now we'll bring the router back in here at 3 inches, and of course we don't want to cut that full depth of that plunge. We want to do this in a couple passes depending upon the size of your bit. We're going to make this in a couple passes. Now let's talk first about climb milling versus undercutting. The router rotates in a clockwise direction like so, and in some cases on the edge of a workpiece it can be like a tire running on the road, and it will then run. If you're undercutting, you're actually going to be tearing the material up, so it's not the cleanest cut, but it gives you more control. In this case, what we're going to do is show you just real quickly here what you don't want to do when it climb mills on the edge. Watch this. Now, do not try that at home. You can see it's quite a trick. Two things you want to remember here. Climb milling gives you the cleaner cut. Undercutting, if you do that, you want to just take several passes and control the cut. Okay? Now, if you want to climb mill, the thing to do is to lock the split nut onto the lead screw and either drive it with the handle, or you can actually turn the motor on, right? And let the motor drive it down the length. Well, now that you know what not to do, let's go ahead and make the cut. Now we're going to use bit number 1274 and position it at 2 1/8 inches. Now because this cut's being made down the center of the material, we don't have to worry about climb milling versus undercutting, because in truth half of the bit is climb milling, the other half is undercutting. So you can cut either end. Now of course we want to do this in a couple passes. And you can see we can make all kinds of different moldings of different styles. On the Fast Start video, you'll see how to make parallel flutes, and on the video that shows the template follower, you'll see how to make dental molding.